Okay, so fine. So we are here for a doubt clearing session based upon the video lectures that were uploaded this week. I hope you have all been able to go through those lectures, and the floor is open for doubts. Yeah, go ahead. I mean, if you have to ask any doubts, yeah, go ahead. Yes, Sai Krishna.
Yes, sir. So I have a doubt in bilinear interpolation.
Hmm.
So it was said that we will actually go from the target to source, right?
Correct.
Initially, and you said we will take that R transpose, that matrix transpose for that. But how will we decide what the R matrix will be initially only?
Wait a minute. See, whatever is that particular this one a transformation, right? That you ought to know. For example, okay, if you know that from the source to target, right, there must be a transformation, right? That has been applied. Correct. It could be a simple rotation. For example, could be a simple in-plane rotation, but rotation can be a complex thing, more complex than just a simple in-plane rotation, whatever it is, right? So the entire transformation rate that you need to know that, and when you want to come back from target to source, you will just have to find the inverse of that transformation.
So, but
And once you have the transformation in the inverse, okay, right? That is what you will use to map the pixels back into the source grid.
okay, so for rotation, it's like we already know the matrix is like that cos theta, sin theta, the
Yes.
fixed matrix. So
Yes. Yeah. You should know the transformation. Here we assume that you know the transformation. In a more complex problem, you have to find the transformation. Okay.
yes.
So what happens is you have to get what are called feature correspondences. Okay, between the two images. I mean, yeah, right. That is something that I will actually talk about later. But in the first set of lectures, we just assume that somebody gives you the transformation, and you just have to use that. So they have told you exactly what it is.
Okay, sir. Yeah, thank you so much.
Other questions? Huh. Yes, Abhishek.
Sir, am I audible, sir?
Yeah. Yes, you are.
Sir, so there's not a doubt per se. So in the second lecture where you were like talking about the applications, you were referring to this thing, the mosaic, like the mosaicing, like using. You said that there's some like when we try using the panorama for nearby objects, like some issue happens. So I actually tried that. Are you talking about like like for example, the image, like it kind of shrinks or like stretches or something like that? Like was that what you were referring to, sir?
Well, I think if I remember correctly, it is a parallax problem that I must have mentioned, the parallax issue. So the mosaicing algorithm, right? What it assumes is that there is a linear transformation, a single linear transformation that allows you to relate the images. For example, you take from one viewpoint, and then you take the image from another viewpoint. Okay, right? Then it assumes that these two images can be related by a simple linear transformation. That means you can go from one coordinate to the or in one image to the other to the say to the I mean of that particular, let's say, point. You can find out where it goes in the second image. So you have a transformation that tells you that. Now, when you have a general 3D scene, right, what I meant was if you're translating a camera, okay, and trying to capture multiple pictures, and you want to stitch them together, what I meant was when there is a discontinuity in depth, which is significant,
Oh.
in the sense that something is in the front. Let's say I try this inside a classroom, right? Imagine a classroom, right? I'm standing with my camera, and there is a boy sitting in the front row, and there is somebody sitting in the back row. Now, if I translate my camera, then what will happen is because there is a difference in depth, so what it'll create is a parallax effect,
Like
which
the
basically,
back row guy will be unaffected, but
yeah, will be less affected. Let's say, right, he will be less
yeah, yes.
affected, whereas the guy in the front will be a lot more affected. Okay, and now and then, right, this is if you have just to see two layers. when think of a scene as comprising of multiple layered depths, right? Then each layer will try to move according to its own depth from the camera, right? Now what will happen is, now there is no single linear transformation that you can apply, okay, which will satisfy this the one that I said, right, which will allow you to map every point in one image to the
Yeah.
corresponding point in the other image. Okay, that's what I meant. So if you try doing that, I mean, that's what mosaicing these cameras will try to do. They'll find some transformation, right? Whatever is the best fit, but that will not be a best fit for the entire scene, and therefore, right, when you stitch it, it'll look odd.
Like, sir, to like add on, sir. So let's say instead of like translating, we just try like rotating around a point. Then that shouldn't be.
That is not a problem.
Yeah.
Yeah. If it's a pure rotation, it's not a problem. But if you're translating, then it's a problem. But generally, yeah, you could. But then people like to typically translate, right? I mean, they would like to do what is called a sweeping motion or what is called a pan motion. But if it's a pure rotation, then there's no problem. You can even pan, okay, such that you pan about an axis. It's simply a rotation about an axis. Then there's no problem. As long as you don't shift the center of the camera, right? You're fine.
Yes.
And I'm assuming that what you're referring to is even if the scene is a 3D scene, that's what you're referring to, right?
Yes, sir.
Yeah. Because if it's a planar scene, then there's no issue. You can translate and then also, right? Then also there is no problem. If it's a 3D scene, then there is a constraint as to when you can mosaic and when you cannot. It's not like it's impossible, okay? I mean, right? I mean, you'll have to have multiple transformations that you'll have to figure out, and then it can still be done. But just that the simple algorithms won't work.
Yes.
What else?
Hello, sir.
Yeah.
Sir, I'm just curious about how do the slow motion video works? Is it somewhat related to like frame FPS?
Yeah. It's a high FPS. See, for example, right? Imagine that, right? You capture at a certain frame rate, right? A particular action. Okay, in a scene. Now, if you drop the in between frames, right? Suppose I drop every alternate frame. Suppose I drop, right, and I kind of play the video. How will it look like? I mean, will it not look like a very sort of a jumpy kind of video where the action happens too fast, right? I mean, because you've dropped some every alternate frame, right? So if you see a bullet passing from left to right, then right, it'll appear like a jerky motion, right? Now, when you want a very, very smooth motion, then what you have to do is do the opposite, right? You have to capture a dense set of frames, or in a sense, you have to kind of sample, right, very, very fine in time. And if you can do that, then what you will have is a high FPS camera. There are high FPS cameras that can do up to 1,000 frames per second, and all those are available now. But the ones that you use are like, so what camera is good for what situation, right? It depends upon what kind of an activity, right, you plan to capture. Especially if it's a dynamic activity, then the frame rate matters. Otherwise, it's not such a serious concern. But normally, yeah, I mean, most of the things that happen in life have a dynamics associated with them, right? And therefore it matters.
Yes, sir. Thank you.
I know the first week of lectures probably, right, you may not have too many doubts, but that's okay. I still felt we should meet and see if there are doubts. Kranti, should we also open up a discussion forum or something just for them to shoot off their doubts? And do we do that? I mean, normally.
Yeah, we usually do that, sir, and I'll create a forum.
Oh, we do that? I mean, even for the lectures, we do that. I thought we do that for the labs. Do we also do for the weekly lectures?
Yeah, we create one discussion forum for lecture, for all lectures.
Oh, so they can post their doubts there and then it gets clarified, huh?
Yes, sir.
I see.
I'll create it now. It's not there now.
Oh, okay.
So I had a general question
Hmm.
regarding long exposure photography.
Hmm.
So how is the memory allocated in long exposure, like very long exposure photography like astrophotography and all?
What exactly do you mean by that? How is the memory allocated means?
So like in a sensor,
Hmm.
the light is captured for a very long time.
Hmm.
So what exactly happens? What exactly is being stored in the memory by the sensor throughout that long period of time?
Well, so what
Okay.
happens is these are all photo receptive sensors, right? So your sensor is actually trying to get as many photons, right, as you can, and especially when things are very very far away, right? The amount of photons that really right, number of photons rather, right, that would hit your sensor, it would be probably a very small fraction. Right? So you have to wait for a really long time, right, in order to be able to get enough number of photons. And those photons, right? Now, once you gather enough number of photons, then the photons are converted into an say electrical signal, right? And then, right, those things are read out as you would read out. Any other image. The only thing would be that you would have to wait for a really long time because you are looking at very very weak sort of signal, right? Because it's very far away, and therefore, right? When you do this kind of which means that you have to have very long sort of right exposures, and there maybe you can afford long exposures because you're not running into issues of saturation or you're not running into issues of some right moving objects and so on. Therefore, it is okay for you to be able to keep. So the memory part, I do not know what exactly you mean by the memory because my own feeling is once you have stored it, then I guess it gets read out the way any other image, whether the way it gets read out for any other image. But I don't know whether you have something else in mind that you're not
Yes,
explaining right now.
understood. So I think memory is separate. The photons hitting the sensors are very low. Therefore, you have to wait a long time to
Exactly.
sample all of them.
Exactly. Or let's
Yes.
say, right? No, let's not say all of them, right? You to sample,
Yeah.
enough number of them. Yeah.
Enough number. Yes, sir. Yeah. Understood.
Sir, is rolling shutter is an effect cost or is it a type of camera itself?
Sorry, say that again.
Rolling shutter,
Ah.
is it a type of different type of camera or is it an effect caused by some distortion?
Well, rolling shutter is actually a camera, a type of camera. See, the cameras that we currently use are mostly of that type, okay? A rolling shutter, it has certain advantages over what is called a global shutter camera, right? A global shutter means that all the rows, right, or all the, okay, sensors, for example, let's say all the sensors in your image plane, right, they get exposed at the same time in the sense that whatever action happens, if there is an action in the scene, so rolling shutter and all really matters only whether you have a global shutter or a rolling shutter, right? Depends upon whether it really matters or not, right? Depends upon the scene. Now, if you have some things going on in the scene, right? If there is an activity, like I said, if there is some motion and stuff going on, or maybe your own camera is undergoing some kind of motion, perhaps you're capturing the scene from some platform or something, right? A moving platform or whatever, right? Then what would happen is, right, in a global shutter, all the sensors see the same motion, okay, at any point of time, right? And therefore, when the shutter snaps, right, they would also, in a sense, right, what you could think of is right motion. Well, how to put it? So you can imagine that whatever motion happened, right, it was the same, right? It was all of them experience the same motion. But in a rolling shutter camera, right, what happens is because you expose, right, one row at a time, right? In the sense that, right, you don't really expose all these sensors at the same time, right? So what can happen is technically speaking, right, you can still have some common motion across a few rows. Okay, because it's like saying that, let us say, right, I mean, if you have an exposure time, let's say T subscript E, or let's say T, right, T is an exposure time, then when you expose the first row is exposed from 0 to T, okay, time, okay, that's your exposure time, and that is fixed for all the rows. Now the see next guy, right, I mean, okay, right, next row will start exposing itself from a time T plus, let's say, a delta T, where the delta T is typically a readout time. Now the next guy starts from T plus, starts from actually, right, delta T to T plus delta T. Okay, now, and then the third row will start from 2 delta T, 2 T plus 2 dt, right? I mean, so you see that the exposure time is the same, but then the window, right, that each row is seeing is not the same, the window of activity. Now, if the scene is static, right, it really, right, would not really, right, it would not really matter. I mean, so which was, because the scene is static, nothing happened. But if there was a motion, right, then what would happen is, let's say, imagine that you have a to and fro motion. Right, then maybe what can happen is when the first row sees it, right, and what the first row sees is not exactly identical to what the second row sees, and what the second row sees is not exactly identical to what the, let's say, right, row number 3 sees. There could be some portions, as you can imagine, right, there could be some portions where they see common things, but there are portions that the first row saw which the second row did not see, the second row saw which the first row did not see, and so on, right? So which is why it is a function of the camera, right, the way the image is captured. So it's not a distortion. Well, it is also a distortion. It can lead to a distortion. Okay, it can lead to a distortion if there is too much activity in the scene. I mean, if the scene is a high, if it's if it's a high activity scene, right, imagine something happening too rapidly, then it could create a distortion, what is called a rolling shutter effect. But then most of the time, right, I mean, you may not have a problem, but then there are lots of works that do kind of deal with this issue. So it can translate into a distortion, but the root cause of it is coming from the way the shutter is operated.
Okay, sir. Thank you.
And go ahead.
How is the spatial resolution being affected by short noise?
How is the spatial resolution being affected by short noise? So the point is this, right? I mean, if you have a low resolution sensor, okay, that means that you have a sensor area, right, which is, let's say, comparatively larger, right, comparatively larger than a high resolution sensor. Correct. Now imagine that, right, if you had a bucket, right, which was small, and imagine a bucket, right, which was large, and if you try to get some raindrops, when you have a larger bucket, right, then it means that so it means that that the likelihood, right, that you'll gather more raindrops, right, is higher. Whereas if you have a smaller bucket, right, then it means that the possibility, right, that you will gather enough number of raindrops, right, is lower. So in the same way, when you have a low resolution sensor, right, so because your sensor area is large, right, you can get more number of photons. Whereas when you have a very high resolution picture, right, which means that your sensor area is very small, right, then you will gather, your uncertainty is higher. However, if you wait enough, right, in the sense that all of this is again tied to the exposure time, right? So if you keep the same exposure time, then on the average you will get lesser photons for a high resolution picture as compared to a low resolution picture. But then, right? I mean, if you kind of manipulate the exposure time, right? Then right? It shouldn't matter. I mean, you can still get a high resolution picture that looks good. Does that answer your question? Or you still
Yes,
have
sir.
some
Thank
doubts?
you.
Which is also the reason why a high resolution picture is more sensitive to, right, motion blur, because you have to probably wait a little longer, and within that time if something happens, right, then the averaging will start to happen. No, and when that averaging happens, right, then you will end up with a smeared picture. So all these are interrelated. I think I do mention that. Okay, these three phenomena, right? Spatial resolution, short noise, and the motion blur. These are kind of all interrelated.
You mentioned that all the transformation models that we're discussing is valid only for a pinhole camera. I mean, as far as maybe at least simple translations or in-plane rotations, I mean, how does the difference come out in terms of a lens versus a pinhole?
See, as long as the lens is able to bring the entire scene into focus, right? For example, if you have a depth of field for the lens, right, which is let's say, right, relatively high, okay, as compared to, for example, the sensitivity of the lens, right, with respect to its focusing ability, then, right, it won't really matter. What you see will look absolutely focused, right? And you can even think of that as equivalent to really, right, a pinhole image. The problem comes when you don't have that, and when you have a depth of field, right, which is small. Okay, for example, if you think about a microscope, right? That is an extreme case, right? A microscope can have a depth of field running into microns, which means that if I keep any object under it, right, and even a very very so let's say even a wafer kind of thing, right, a silicon wafer, then even something like a wafer, right, which could be just a few microns thick, right, you won't be able to bring the entire wafer into focus because of the sensitivity, okay, with respect to a change in depth. So in such cases, right, a pinhole model, right, is still valid. I mean, in the sense that the central ray, I mean, right, this is something that I talk about later. Okay, this is a question that's come a little too early, but as long as you see the nice thing is that, right, I mean, since the model remains linear, right, everything can still be done. Okay, it's not like the moment you go to lens, right, these equations will fall apart. Okay, they don't. And in fact, a projection equation that the central ray, right, I mean, that a pinhole ray follows, is actually followed by the central ray, right, when you actually use a lens. And all that happens is the intensity spreads around that ray when you have blur, and it remains a point, right, when let's say things are absolutely in focus. And therefore, right, one can still kind of relate images, but normally, right, people don't talk about it much because, right, I mean, I haven't seen too many papers that really talk about, a blurred image being rotated, translated, and so on. But yes, yeah, it can happen. And then you may still want to kind of talk about how to kind of relate them. The problem occurs because the intensity spreads, right? The intensity spreads. And which is why when you change from one location to another, the spread is not the same, right? So for example, if a depth changes with respect to the object when you move from point A to point B, then right, what will happen is even the spread of the intensity will change, what is called a blur circle. And therefore, right, matching the points and all becomes very, 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 very tricky, because it doesn't even make sense to ask what to match with what. Because the intensity, the photometric information itself undergoes a change. See, a pinhole, right, the nice thing about a pinhole is that the photometric information sort of remains intact. So if you have an intensity of 155 at some location, right, then you can sort of expect, right, when you translate the camera, you can expect let's say, right, 155 at in the second image at some other location, right, which you can hope to reach through a transformation. But that's not the case when you have a lens where there is a defocusing effect.
So you're basically saying when in a pinhole camera, I mean, you sort of have a point-to-point mapping between the image and the sensor plane, the scene and the sensor plane. Whereas in a lens, it's not like that.
No. Wait a minute, right? I'm not saying that right. I mean that you know what? I mean you can't. You don't know where a point is going. You still know where the point is going. All that I'm saying is the intensity, right, no longer remains the same. Okay, so to sort of talk about points, right, in terms of intensities, right, becomes tricky. A location where it goes, you know, basically, right, where it goes. But what will be the intensity there depends upon the new depth, the lens parameters, how it got blurred, what other intensities came right, I mean, into that location, because you can have blur circles interacting with each other. That's what I mean. Not clear?
Roughly. I mean, I guess, are you alluding to something like vignetting or
No.
the intensity stage?
I'm just talking about simple this one, right? The effect of blur caused by lens. Anyway, right, when we do real aperture cameras, right, which will come up, right, down the line, at that time I think, right, things will be more clear, because right now, even if I try to explain, right, it'll still remain a little murky. See, for example, I mean, right, see, suppose I ask you, right, I mean, if I mean, right, one of the examples, right, which we kept saying was that in order to be able to do this transformation was to, let's say, right, compare images. And we said take a picture of IIT Madras, right, on one day, and then take it on another day, and then, right, compare the two images, apply the linear transformation, align them. Okay, now suppose I told you that, let's say, right, if image 1 is also blurred and so is image 2, and then the blurring is not the same, even though the camera might be the same. Okay, even for the same, even of course, typically you may not even have the same camera, but even if you had the same camera, right, depending upon where it was taken from, the image, the kind of blur that gets induced in the image is not the same. Now, if I ask you compare the two, what would you do, right? Because the photometric information is no longer the same, right? So what does it even mean to align them and subtract them and all? Do you see are you able to get to what are you able to get what I'm telling?
You're saying even if you took the same camera with the same focus settings and I mean all of that, I mean, even if you had the exact same configuration, you'll have different blur. Or
yeah,
exactly. If there was different, I mean, you mean blur, you can talk about maybe defocus or motion blur or something like that. I mean, defocus blur probably is the same.
No,
but motion blur maybe it can change.
No. Defocus blur will also change. Defocus blur is after all a function of the depth of a point from the lens. So if you have moved, right, that depth has already changed for the same point. You've moved, you're taking from another location. I'm not even talking about motion blur and all. Let's forget about motion blur. Talking about pure optical blur. Optical blur does not remain the same.
Okay, when you translate a scene, I mean, even if you're doing an in-plane translation, the depth corresponding to different pixels can be different. Okay.
So, which is why, right, people, what they normally do is de-blur it, or what you should be able to do is find out what is the relative blurring, right, that you need to apply between the two, so that the two look alike photometrically. Right? So yeah, that's what I'm saying. Right? So it's more I mean, this is not simple. The moment you get the lens into the picture, and if you assume that scenes are defocused, right, then those kind of approaches are quite few. Okay, so one thing people will do is write a deblur so that you get focused images from both and then you move on. But then you don't have to do that. I mean, you can directly try to solve it, right? What is called reblurring, right? And not kind of deblurring, right? You can do what is called reblurring, but that's not so easy. Neither is easy. Even deblurring is not easy, and reblurring is also not easy. Any other doubts?
Sir, in the second lecture, we talked about halving the spatial resolution. Does it mean we take first 4 pixels and average them out to get half the resolution of the original picture?
Yeah, exactly, right. That is the interpretation when you kind of talk in terms of sensors. See, for example, in 1D signals, right, you could just pick alternate samples. Even in images, right, some people model it like that. Like, for example, right, you could skip the intensities in between. But in reality, right, that is not the one which simulates the effect of a low resolution sensor. By low resolution sensor, we mean that we are packing fewer number of sensors within the same area, which means that your sensor area is now larger. And therefore, when your sensor area, right, is larger, right, then it actually means that for a high resolution guy, that same sensor area you can further split into 4, and then for each of those boxes, right, you can get one intensity. Whereas if you have just replace the 4 by one sensor, that means what you'll get is an average. Whether the average should be equally weighted or should it not be equally weighted is actually a different issue. But normally, simplest model is equally weighted.
Yes, sir, like I got it in terms of how we capture it, and I want to just understand how it is done in terms of displaying. Like, let's say take a YouTube video, like when the internet bitrate transfer is kind of low, it will be a low resolution one, whereas when the number of bits coming through are high, like it transfers to a higher resolution. It's like how that is kind of done.
Oh, there I think the simplest thing which they would do is skip, because I mean, why would you want to average and lose information?
Okay.
I was talking about a physical.
Yeah, I understood how capturing happens. Yeah, that I got it.
Yeah,
like this side, it seems kind of the invert to what we are talking in terms of capturing.
Right. But if you already have a picture that is high resolution, and then it's simply because you're running into bandwidth issues, right? You wouldn't want to average. I mean, at least every alternate pixel intensity you can send.
Yes, it got.
Yeah, I just wanted to tell you guys that okay, I have to talk to my TAs. Okay, Kranti is here. We'll have to talk about. See, the first quiz, right? I was referring to, what was that, January 29th or something, right? Next Saturday. But I think we may have to start the Saturday after that. Okay, the first quiz. Because I mean, I have to check as to how much we cover and whether we'll have enough to ask for the first quiz. Okay, I have to kind of do that homework. I was assuming that, right, we'll have it. The second reason is that the quiz will come up immediately the day after Friday, right? Because we keep it on a Saturday. So I was wondering whether it's better to sort of, what do you call, shift it by a week, so that from there onwards, right, you have like a 1 week gap, right, between the contents that were uploaded and the time and the time that you appear for the exam. Right. So I need to kind of look into those issues, and I have to see as to which one is a kind of best fit. But we'll send out a mail well in advance, so that, right, we won't keep you in suspense till Friday or something. I think by next week or by early next week, we'll send out a mail saying whether the quizzes will start from 29th or from the first week of Feb. But once started, it'll keep going on a sort of routine basis, alternate weeks and then alternate Saturdays it should come. And also lab assignment also, I think we will probably upload next Friday, because we typically upload it on a Friday by 12 noon, the lab assignment, and then we expect you to submit by the Sunday, which is like 8 days away or 9 days away. Okay, that Sunday midnight or something is when we'll expect you to submit. And the way we are planning it is, you will submit, okay, a PDF along right with the codes. You'll upload it to Moodle. I think we'll create a folder where you can upload your code and your file and your output obviously results. And but then the one-on-one, right, interaction which I mentioned that our TAs will have with you, just to understand, right, whether you understood what you did. So that may happen like once you complete 3 assignments. Okay, so that 3 can be taken up in one go, because we don't want too much time being spent from your side as well as from our side, because otherwise what will happen is every week to get a slot, with so many people is not going to be easy. So we thought once 3 labs are uploaded, the week right after that, the week that comes immediately after that is when the evaluation should happen for all 3 labs. But a hard deadline will be like for you to submit the codes and submit a PDF. Okay, that cannot be changed after that. And all that the TAs will do is ask you as to how you did each one of those labs. They'll set up a Google Meet or whatever is convenient. Okay, any other doubts? Okay, if there are none, then maybe we can stop here, and then I think we will actually send out those mails to you, okay, as soon as possible. All right. I mean, I'm assuming that there are no more doubts. I mean, I can wait for a minute. All right. Okay, then. See you guys next week. Bye.